Now we're going to talk about some general reactions that you're going to see in the context of sugars. Now some of these reactions you're going to want to look at when you're dealing with the Haworth projection, and some of these you're going to want to look at when you're dealing with the Fisher projection. So let's start with the ones that deal with Haworth projections. So I'm just going to draw a generic Haworth projection. Let's say we'll do a 6-membered ring. So an aldopentose, put an OH here, an OH there, an OH there, an OH there, and an OH there. And now I'm just arbitrarily putting these OHs this way. Just going to talk about them each individually. So the reactions that involve the Haworth projections will be these: CH3OH with H plus, or any carbon chain OH with H plus. CH3I. These will typically involve the Fisher projections, so Fisher, Fisher. The protecting group is typically used with the Haworth projection, and the rough degradation and the Kalani-Fisher synthesis are typically involved with the Fisher projection. So the H's are the ones that you need to use the Haworth for, and the F's are the one for the Fisher projections. And if you start with a Haworth projection but need to do a reaction that involves the Fisher projection, you have to convert first, and vice versa. If you're doing a reaction that needs to work with a Haworth, but you start with the Fisher projection, convert it to the Haworth first. Okay, so let's start with the CH3OH reaction. What the CH3OH reaction does is it takes whatever the OH carbon chain group is and replaces your anomeric OH with that group. This reaction only affects the anomeric OH. So this carbon OH over here. So if I were to take this ring and react it with, say, let's say a really long carbon chain with a double bond on it, and then there's no OH over here. So I have 1, 2, 3, 4 carbons. What I would expect to get at the end of this is my ring virtually unchanged. All the OHs, aside from the anomeric carbon, will remain exactly the same. Or rather, the anomeric OH will remain exactly the same. So these 4 are exactly the same, but now the anomeric OH will have this oxygen and the whole carbon chain attached to it as well. So oxygen and then 1, 2, 3, 4 double bond. Okay? Now, the mechanism of this I will probably draw out in a separate video, but because of its mechanism, the stereochemistry of the anomeric carbon can either be up or down. It's going to end up changing through this mechanism, because what you end up doing is, I guess I'll draw it out here, it makes more sense to do that now. What ends up happening is this OH would get protonated by your acid, because typically it's an H+, so you have an H2O positive over here. And now the oxygen in the ring is going to swing down, kicking that H2O out. And so you'd be left with, I'm not going to draw on the other OHs, I'm going to focus on the anomeric because that's all that matters. You'd be left with a double bond O positive there. And now whatever oxygen group is over the arrow, so in this case the OH with the carbon chain and the double bond, will come in and attack the base of that double bond, pushing the electrons up. And remember, whenever you make an attack on a double bond that's flat, whenever you make an attack on a double bond that's flat, you can attack from the front or the back. And in this case, that means up or down. So there's no way to predict whether this thing attaches pointing up or pointing down. I arbitrarily drew it pointing up, but technically there's another possibility where it's pointing down, and you would get both, arguably. But that's the idea behind this. Whenever you see a carbon chain or a carbon group with OH and then H+, all you're doing is replacing the anomeric OH with that oxygen and whatever carbons it is attached to. Okay? CH3I is the crazy fun one because he doesn't care which OH you're using, he's going to react with all of them. So let's keep this here. So what CH3, sorry, not CH3OH, what CH3I does, when that's over the arrow, remember iodine is a really, really, really good leaving group. And that means anything with electrons will be inclined to attack that carbon and kick the iodine out. That means every single one of these OHs is going to react with that CH3I. Let's start with one like the anomeric OH. The oxygen will attack the carbon and the iodine gets kicked out. And now you have this oxygen being an OCH3. But unlike the carbon chain OH reactions, this will react with every single OH, not just limited to the anomeric, which means the final product here will be every single oxygen becoming an OCH3, or an O whatever the carbon chain is attached to the iodine. Okay? So that would be what you get if you use CH3 iodine. Now, what if we want to get rid of those CH3 groups? Well, unfortunately, once you get OCH3 on any of these carbons, there's no real way of going back, not that we're going to teach at least, or none that I'm familiar with. But you can always convert your anomeric carbon back to an OH, or rather your this anomeric oxygen, whether it's OCH3 or OH, can always be turned back into an OH, and you do that by using H3O positive. So if I were to take this one step further and say H3O plus, all of these OCH3 groups would remain the same, except for the OCH3 group that is your anomeric oxygen. And so if I took that H3O positive step, I would get this oxygen becoming an OH again, and then every single other oxygen being an OCH3. Okay? So this works for just the CH3 oxygen or CH3OH reaction as well. You can reverse it, turn that anomeric OH back into an OH by using H3O positive. But again, H3O positive will only affect the anomeric OH. These guys remain unchanged. They will stay in their OCH3 forms. The final reaction that involves the Haworth projection is your protecting group. And sometimes Professor Grubb seems to be fairly fond of synthesis problems involving sugars. And so you may end up having to use a protecting group. Now, what are the rules involving this protecting group? First of all, let's go back to exam 2 material, because that's the first time we saw this protecting group. That was OrgoBeast, right? Now, what OrgoBeast does is it takes two alcohols and basically combines them to one carbon. And I'll draw that out in a second, so it's probably easier to visualize than just by word alone. So for now, I'm just going to draw the same thing and we'll fix it in a second. Okay. So the next thing over the arrow we're going to be dealing with is the acetal protecting group, OrgoBeast, with H+. Okay. So what this does is it takes a diol and connects the oxygens of the diol to this carbon, and this oxygen will be gone. Now, there's an important rule that you need to know about this protecting group, and that is if you're going to protect any of the OHs on your, if you're going to use a diol to protect, if you're going to use a diol to react with this, the OHs that you use from the sugar ring have to be pointing in the same direction. So if I look at this OH is pointing up, or sorry, I should be using this. This OH is pointing up, this OH is pointing down. They're pointing in opposite directions, which means that these won't get protected. These OHs are pointing in the same direction, so this would work, but I'm going to go further to make a point. This is pointing down, and this is pointing up. They're in opposite directions, so the protecting group wouldn't be able to protect these two. And this is too far away because it's 1, 2, 3, so we can't even consider that OH. These are the only two OHs that could ever react with that because they are a single bond apart and pointing in the same direction. So that means what you're going to do is you're going to see, well, whatever carbons are on this carbonyl, all you're going to do is you're going to redraw the carbonyl over here between the two OHs that are going to be part of the protecting group. What you're now going to do is erase the double bond oxygen in its entirety, erase the hydrogens of the two OHs, and connect the oxygens to those carbons. And now you have those two OHs protected. So if you use a reaction like CH3I, these oxygens wouldn't become OCH3s. In fact, let's draw that out. What would that look like? So I do CH3I in my next arrow. Well, that would mean this OH, and this OH all become OCH3s. Oxygen, So this is an OCH3. These carbons or these oxygens are still in the protecting group. And then this OH is pointing up, and this CH2OH, sorry, this should be an OCH3, and this should be an OCH3. Okay? And now what would happen if I treat this with H3O positive? Well, remember, H3O positive has a couple things it can do in a sugar. First of all, it can turn the anomeric oxygen back into an OH. So that'll definitely be one thing that people do. So I'm going to draw this in red so we can see it better. Oxygen. So this is an OH again. But these OCH3s we said can't get affected by that reaction. So they're still OCH3. And this is OCH3. But now remember, the other thing we learned from exam 2 is that H3O positive removes your protecting group, which means what I'm going to do going to this is erase these carbon bonds and just turn these back into OHs, still pointing both down. So I would get this at the end. These oxygens, because they were protected, did not get reacted with the CH3I reaction. So that is how and when you would want to use a protecting group if you want to convert some things into OCH3s, but not two that are pointing in the same direction. I know that's a little specific, but in a synthesis problem, we're usually going to be specific like that.